Hey everybody, my name is Gian Merlino. I'm a metrics enthusiast. I also work on the Druid project. I'm kind of curious, how many of you guys have heard of Druid before? Whoa, that's more than I expected, that's awesome. How many actually use it in production? Cool, you're my hero. Anyway, so I want to talk a little bit about Druid, what it is, where it came from, and how I think it fits into the whole monitoring world, which is not really what it was originally built for, but it's something that's near and dear to my heart. I'm a reformed DevOps guy. I used to work at Yahoo on server configuration management and provisioning. Now I work on sort of big data, database stuff, but still remember my roots. And I think that I'm pretty excited about taking some of these ideas from big data and these ideas from databases and analytic databases and applying them to monitoring. So what I want to talk about today, first where Druid came from, then how it works. There's a little bit about internals and stuff like that, how you can use it. Mini workshop. I don't have a demo prepared, but I do have a cool GitHub repo you can check out. I want to show some visualizations powered by Druid, and then talk about the future of Druid and where we're going with the project. So first, where Druid came from. I think it's important to sort of understand where technologies come from to give you a sense of the people that made them and what they were intended to be used for. So Druid was developed at a startup called Metamarkets a few years ago to do analytics for online advertising. So the problem that we were trying to solve in Metamarkets was you have, if you have a web browser and you use the internet and you don't have ad block for some reason, you've probably seen things like this on websites. If you have ad block, this is called an ad. This one in particular is trying to sell a mortgage to you. And what the advertiser hopes you do is click on it, and then you go to a website like this. And you can see I opened it in incognito mode because I'm scared. And what they really hope you do, if they're very picky, is actually buy something. This happens very rarely, but it does happen often enough to pay the salaries of a whole bunch of people. So the analytics for this is basically we're going to look at what people are seeing, what people are clicking on, what people are actually buying, and try to find some patterns there to try to make people more money. Specifically, technically, the problem is arbitrary interactive exploration. You can think of it as sort of like a slice and dice drill down tool for big data. We're really interested in multi-tenancy. So we want to support thousands of concurrent users on a single cluster. At Metamarkets, and actually in most Druid deployments, you have a ton of data all thrown in the same cluster. Recency is really important. New data is generally more valuable than old data. You want to alert on major changes and explore things as they happen. And efficiency is also important. In the world of online advertising, this also applies to monitoring. Each individual event is very low value. You don't really care what CPU number 8 is doing on some random server, but you do care what the CPU is doing across an aggregate of servers. And the final thing is scale. So for this online advertising data, we have petabytes of raw data represented in the cluster. And if you look at time series metrics, you can generate a similar amount of data if you have enough metrics and get really greedy with the kind of things you're trying to measure. So the way that we wanted to let people analyze this data is through asking a series of questions. And the idea is that questions lead to more questions. The idea is you're not just interested in what happened, but why it happened. And the way you figure out why something happened is you dig into your data set using filters, aggregates, comparisons, try to just get a shape of what's happening in your data, try to understand it by playing with it. Because you're trying to play with it, you want queries to happen really quickly, and also you can't determine all of the interesting queries up front. You don't necessarily know what people are going to want to play with to understand their data. So it's important to avoid pre-computation. So that brings us to Druid, which we made to solve these kinds of problems. The Druid project started in 2011, and it went open source in 2012. It's an event stream database. It's not a time series database, but it's kind of like a time series database, but it's also kind of not, and I'll talk more about that later. It's designed to do low latency ingestion, and that's just I don't know, it's important. It's also designed to do ad hoc aggregations, and that's that exploratory thing, that's the interactive thing, avoiding pre-computation. It's also designed to keep around a lot of history. So A lot of Druid deployments keep around years of history, and that's okay. Development is community driven. This isn't sort of just one company developing it, making it open source. It's actually, we're trying to build a community around it. So we have 90 contributors, over 90 contributors now, and it's in production. We have big deployments at Yahoo, Netflix, and of course the original one at MetaMarkets, and many more. So I want to talk a bit about event streams and why I said Druid's an event stream database and what that means. So the interesting thing about event streams and what they mean is that events happen over time. And the questions you ask about them are often time-oriented in some way. So in monitoring, you may want to know CPU usage over time. In web analytics, you want to know top pages and how they change over time. In performance, you want to look at high percentile latencies recently if you're trying to debug a performance problem. So I also want to talk about what some example event streams may look like, what event data points may look like. This is an example from Wikipedia edit stream. This is an edit that happened at some particular time. The next sort of broken out section of things is what we call dimensions. There are things you can filter on. They're like string tags. There are things you can filter on, things you can characters on. And the last thing are the metrics. Those are the things you're taking sums of, averages of, or what have you. So questions we might add to this data set are, what's the average byte size in edit? We may want to know what are the most popular pages being edited in a particular country. We may want to know who the most prolific users are. We may want to just see a distribution of users so we understand, is Wikipedia the kind of place where a small number of users dominate or where a large number of users are making most of the edits? Here's another example of an event stream. This is sort of a web activity example. This is me editing my profile on some unnamed app of some kind. I edited my email on my phone, and the host, the backend host that handled my request was this host one. This data set is probably being used for some sort of latency analysis, and so the metrics for it have the response latency and the number of bytes in the response. So we may want to know things from this, like what's the 99th percentile latency for a particular host, broken down by host. We might want to know the slowest host so we can find our problem host. We might want to know the slowest actions so we can figure out if there's a feature in the app that's causing problems. We may want to know latency per byte, if that's interesting. So the next thing I want to talk about is time series. And I said Druid is not a time series database, but time series are still interesting. So in time series, you're measuring your world with some resolution. And the measurements of your world take place as data points. Each one has a timestamp. They're generally part of a series, and there may be some tags you include for filtering. So really common classic examples of time series are CPU use, disk use, network traffic. So like I said, Druid is not a time series database, but it's okay because time series are actually event streams. They're event streams where the event is you're measuring something. So we can represent time series as event streams and store them in Druid or any other event stream database. So here's an example of a CPU usage measurement. This is a single measurement, so it takes place at a single point in time for a single CPU. CPU is 0 on a particular host. And we might ask questions of this, like what's the average CPU use across all our hosts? What's the average CPU use across all CPUs on a particular host? What's the distribution of CPU use across CPUs? That was actually interesting in reality to a problem we were facing a couple months back where we were finding that the scheduler was erroneously sort of assigning too much work to the first CPU. And you don't really see that kind of thing in an average, but you do in a distribution. So I'm going to talk a bit now about numbers of Druid in production. So what kind of performance it's capable of and what kind of scale it's capable of. So the biggest known cluster, or the biggest cluster that I'm aware of, is the original one at MetaMarkets. There's a few others out there, especially Yahoo, that are approaching that in size, but I think the one at MetaMarkets is still the biggest. So the ingestion rate of that cluster is averaging about 1 million events per second, and at peak is over 1 million events per second. The performance is per core about 10 to 100,000 events per second. And the reason for that big range is that 100,000 events per second is what you get with very simple data or in benchmarks, and 10,000 events per second is what you get with more complex data in the real world. So the size of that cluster, of that same cluster, is got about a half a petabyte of segments in it. And I said earlier that it represented petabytes of raw data. The reason for the difference is compression and rollup, which I'll talk about in a bit. That's just a strategy for reducing the data size. So that comprises 20 trillion raw events, over 20 trillion raw events. And that cluster has 5,000 cores for chewing through all that data, and a lot of RAM. The data is not all in RAM, but it's a large portion of it is. So the query latencies are pretty good. This is sort of the whole point of the system, is to get good query latencies. When we built this, we weren't really coming at it from the monitoring world. We were coming at it from the big data world, where if you don't need great query latency, you can use something like Hadoop or like Hive or what have you. But if you do need great latency, you have to sort of look to other things. So in that same cluster, the average query returns in less than a second, and even the 90th percentile query returns in less than a second. 95th and 99th percentiles are a little bit slower, but even 99 is 10 seconds, which I think is not too bad given that many queries are scanning millions or billions of rows. So I want to talk a bit now about how you actually use it. The queries are JSON over HTTP, and all computation is pushed down to the data nodes. So the queries received by Druid will sort of be replicated throughout the cluster. The kinds of queries you can do, the first and simplest one is time boundary. It's sort of a very basic query that tells you the oldest and newest data point you have in your cluster, just so you have a sense of what's out there. It's usually used by UIs to sort of initialize their time pickers. The next is time series. Druid doesn't store time series as time series, but it can generate them. So you can tell Druid that you want to generate a time series with a particular granularity from a particular filter set. So you may want to say, I want a 5-minute time series of CPU usage across any host that matches this regex, and Druid will do that. The other query, the most general one, is group by. It's sort of what you think it is. It's really similar to a SQL group by or group by in any other database. And the last one is one that I think is, I'm not sure if anything else out there does that. It might be unique to Druid, an approximate top end. And the way that works is it's like a group by with a limit, but it's much faster. And the way the approximation works is that values near the top of the top end tend to be much more accurate than values near the bottom, which is usually match what you're trying to use the top end for. You're usually most interested in the top whatevers. So you may ask for a top 1,000 of hosts by CPU, and then you're really interested in the top 10 of that, which will generally be pretty accurate. So these are the supported metrics by Druid. You have sort of the basics: count, sum, average, min, and max. You also have some sort of fancier ones. So there's approximate cardinality using hyperloglog, the famous algorithm. And that's usually used for stuff like computing approximate numbers of unique users. There's also an approximate histogram and quantile implementation that we use for generating all the latency numbers you saw earlier, and also just latency analytics in Druid in general. The cool thing about it is you don't have to choose a quantile ahead of time. It sort of stores things as an approximate histogram, and you can use that to generate any quantile you want later. Or you can just generate an actual histogram as a distribution. You can also extend Druid with custom metrics or sketches if you want, and some people have done that. And some people have even opened what they've done. There's a few client libraries. Like I said, the API is JSON over HTTP. But if you want to use a client library rather than just making JSON calls yourself, there's one for Python and R that are pretty popular. There's also one for Ruby. There's a JavaScript one that we actually use at MetaMarkets to build MetaMarkets products. And there's a SQL command line if SQL's your thing. There's more clients for more languages at that link up there. So this is the mini workshop part. Like I said, I don't really have a demo. I was too scared to do a demo, but I did make a cool GitHub repository. This is my sort of first time playing around getting Druid set up with Grafana, which is the only sort of open source free UI that I'm aware of for Druid. I'm going to show some more visualizations later, but they're all sort of things that people have built internally. I don't think I've opened them. So in this GitHub repo, if you check it out, you'll see the README there sort of has instructions, and then the actual files in the repo are config files for the various services. And what it'll get you set up with is using Kafka for ingestion, One of the guys talked about Kafka earlier in one of the other workshops. I really recommend it if you're not using it for just sort of taking things in and putting them somewhere else. It's really good for that. Using Druid for analytics and using Grafana, of course, for visualization. You'll get a single machine setup when you do that. You could turn it into a distributed setup once you play around with it. It'll just need a bit more configuration, and the docs will help with that. So the last part of the mini workshop, more resources. There's our website, druid.io, and there's also some tutorials on that site that have different tutorials than the one on the GitHub. So now I want to talk a little bit about Druid's internals. I hope there's some database geeks in the audience that are not going to be bored by this. I think it's cool. So internally in Druid, the first thing that happens is little blue squares and some arrows fly around the page. Obviously, the little blue squares represent data, and the arrows represent networks. And they go into something called a real-time node. A real-time node is a kind of node in Druid. Druid is composed of multiple node types. Each does a particular job very well. And the idea behind that is just isolation of resources. So we go into these real-time nodes, which expose the query API. Real-time nodes are designed to ingest event streams, and they let you query data in memory as soon as it's ingested. This is much like every other metric store out there. Periodically, they create and hand off immutable segments. And I'll talk a lot more about those segments in the future. The things they hand off to are called historical nodes. This is the second major node type in Druid. Historical nodes are the main workhorses of a Druid cluster. They store these immutable data segments. They don't accept any writes. They only do reads. They respond to read queries. The final sort of important node type is the broker nodes. Broker nodes are what you would actually talk to when you're making a Druid query. All three of these nodes expose the same Druid query API. You can query any one with the same queries, time series, group by, top n, etc. But generally, you'll be querying the broker nodes. And the reason for that is that broker nodes do not just query data locally on themselves, they also query data located throughout the cluster. So broker nodes know which other nodes hold what data, and they'll incorporate data from the entire cluster using a scatter-gather sort of thing. So they'll find all segments that are related to your query. They'll forward the query down to the nodes that has those segments, which will compute their local results. And then all the broker has to do is do a final merging of results. So I'm going to talk a little bit about how we get these queries so fast. How do we get queries less than a second that are scanning millions or billions of rows? So the real trick, the one weird trick, is that we have two storage engines. Each one is really hyper optimized for what it's supposed to be doing. We don't try to use one storage engine for everything. So the historical nodes I mentioned earlier, I sort of talked about those immutable Druid segments they have. That's all they have on them. So the historical engine is these time-partitioned, immutable, memory-mapped Druid segments. They can be all memory if you want. They are memory maps, and if you can set a configuration per historical node called the max size, and you set that to less than the amount of memory you have, everything will be in memory. If you set it to more than the amount of memory you have, then it'll be partially memory, partially on disk. And it's sort of up to you how you want to tune that. It's a little knob you get to control performance versus cost. Historical nodes only talk to data that they store locally. So they're always computing data locally. And they're generally not streaming data anywhere else. They're generally computing a partial result that's much smaller than the data they actually have. So that limits network transfer. They can do very fast filtering. So there's a global time index that the broker uses to discover which shards or which segments are related to a query. And also within each query, or within each segment, there's indexes for fast filtering. And the big one that we have is either a concise or roaring bitmap index, which is something that's also pretty common in search systems. I think Elastic and Lucene use something similar. Once Druid's found which rows it's interested in using those filters, it can then scan those rows very quickly. It's those columns, it's column-oriented, which are all compressed, and those two sort of work together to make scans very rapid. And I'll talk more about that in a bit and go into like what the columns actually look like. But before then, the other storage engine is the real-time storage engine. The real-time engine looks a lot like what many other time series databases look like. You have an in-memory key value tree. And then you have these on-disk memory mapped Druid segments that when the in-memory key value tree fills up, they're sort of converted to this on-disk format. And then when you get a query coming in, what you do is you query all the little segments built on disk, and you query the in-memory key value tree, and you merge the results together. And the real-time nodes will do that. This is really similar to how the in-memory mem table and the on-disk SS tables work in RocksDB. But the difference is that rather than being a generic key value store, Druid uses those mapped Druid segments with the column orientation, with the compression, with the filtering for its on-disk format. And so queries are much faster than a generic key value store. So this periodically, the real-time node will take these on-disk things it has, this in-memory thing it has, generate appropriately sized final Druid segments, merge them together, and then hand them off to the historical nodes. So the real-time nodes are really only handling a window of recent data. And we can get away with that because we're trying to handle event streams where almost all of the writes are very recent data. So now I want to talk about what those segments actually look like internally and how the queries are actually done on them. So imagine a raw data set that looks like this. This is an advertising data set. The advertiser and all of these ads impressions, there's 6 impressions that happen here is Google. Google loves ads. There's 2 websites they're advertising on, ultratrimfast.com and beaverfever.com. And so there's 6 ads here. These are 6 events in the event stream. What that'll look like in Druid, along with a lot of other events, so these are now thousands of events rolled up into these 4 rows. They'll be rolled up together, and what that means is with Druid, when you do ingestion, you specify a indexing granularity, a roll-up granularity. And that's just going to truncate timestamps to that granularity. And that granularity will be the finest one that you can query at. So if you want to do time series all the way down to second, but you don't need to do millisecond, then you can truncate to second at ingestion time. What Druid will do after that, after truncating timestamps, they'll group by all of the string columns and then aggregate during ingestion when possible. And what that means, when it is possible, is if you have 2 events that occur in the same granular time window and have the same string dimensions, then they can really be represented in the same row just by adding the metrics together. And so that's what's happened here. You have these 1,800 impressions and 25 clicks means that there's 1,825 events that matched ultratrimfast.com, google.com, Mail USA, and that occurred in that particular hour. So this is a data set that's rolled up to the hour. The other cool thing about this rollup is that you can incrementally update these aggregate rows without any storage overhead. So Druid can actually go into that row and update it without having to write a copy of it. That's nice because you can say something like, well, I only really need time series down to minute resolution, but I want them to be updated every second. And you can do that. So you can send an update with an incremental update to Druid every second, tell it to truncate it to the minute, and what that'll look like is the most recent minute will start at 0, and the metrics will sort of climb over time until that minute is finished. And at the end of that, you'll just have 1 row in Druid. One last thing about that, that's sort of, the number of events that go into a row in Druid is something we usually call the roll-up ratio. And it's pretty common for those to be somewhere between 1:1 and 100:1. And you can imagine that for the data set I was talking about earlier, where we have petabytes of raw data becoming only a few hundred terabytes of Druid segments, a lot of that is because of roll-up. So the average roll-up ratio in that cluster is about 20:1. The next thing Druid does is partitions data by time. So it's an event stream database focusing on time-oriented events. And the idea, the heuristic that we have is that we're assuming that most queries are going to have some sort of time filter. You're generally going to be interested in probably more recent data. There's always some sort of time component to what you're doing. And so splitting shards based on time makes a lot of sense. So we do that, and that's also something that time series databases generally do. Another thing we do is that within each of these segments, the data is stored column-oriented. So that means the data for a particular column is contiguous. So you only have to actually load and scan the data that's related to the query you're actually doing. And this is what lets you get away with not actually having enough memory to store all your data. You may have 30 columns in your data, but most of your queries don't hit all 30 columns, and so you don't necessarily need to have it all in memory. So you can scan and load only where you need. Each column is individually compressed. The string columns are compressed to dictionary encoding, and all columns can be compressed with LZ4. And each column has individual indexes. So the string columns have those concise and roaring bitmap indexes that are used for fast Boolean filtering. Okay, so that's sort of it for the internals part, and now I want to talk about some cool visualizations that are powered by Druid. So the first one I want to talk about is the one at MetaMarkets. So at MetaMarkets, we dog-fooded that business analytics tool as an ops monitoring tool. So internally, all of our metrics, all of our server requests, all of our everything was thrown into our own tool, and we were sort of using that to analyze them. And what that looks like is this. I sort of cut out what's on the right, which is this context panel, just because it had some sensitive stuff in it. But what you would imagine over there is breakdown of latency by host and messages in and out by host and by container and things like that. This is a stream processing monitoring thing that we can use to look at our SAMSA jobs using SAMSA for stream processing. So you see events in, messages in, bytes in, sort of classic stream processing metrics, and also the success rate at the end, which is how many of the messages actually get successfully processed. So this is a stream processing job that's doing pretty well. This is another screenshot of a job that's not doing well, and it's pretty clear from the time series that it's not doing well. You see this offset delta, which is sort of how far behind it is from the source, is climbing, and the success rate is dropping. So there's some failure going on that's causing it to fall behind on its input. And what we would do with this in real life, if we saw this, was, well, one thing we might do is just restart it. If we wanted to figure out what's actually happening, we can use the context panel to sort of look at, well, is the slowness isolated to a particular host? Are the failures on a particular host? Are they in a particular container? Are they on a particular part of the job? So we can drill into any particular dimension we have indexed, and by doing that drill down, we can understand what the problem is. We can also set an alert on this and say, like, if the success rate drops below, 99% or 100%, fire an alert. Okay, so another set of examples are from a company called Quantify. These are also sort of internal UIs that are not open, but I still think they're interesting. Quantify is a financial services company. I never worked there. I got these graphics courtesy of someone that does work there, that the Druid community owes a debt to. His name is Roger Hoover. They have a lot of microservices. They have over 1,000 microservices, and they use Druid to find latency hotspots. So the first visualization they use for that is this latency heat map. So I'm not sure if the labels are super readable, but the bottom two are 0 milliseconds and 1 millisecond. And then the two labels around that band you see are 100 milliseconds to 1 second. And the labels at the top are dates. So you can kind of see that for the majority of the time, this service is returning results in less than 1 millisecond. But at certain times of the day, and it actually looks like kind of the same time every day, the response times spike up into the 100 to 1,000 millisecond range. So to figure out what's going on here, we already know that there's some sort of daily issue happening. It's probably load related. So we can drill into what's actually causing that. One way that they might drill in at Quantify is they made this really cool latency tree map. So this is a latency tree map by service. And what you're seeing here is these boxes are colored per service. They're sized by the total time that service is taking to respond to the overall larger request. So these are a ton of microservices that are involved in a larger request. And they're colored by the deviation from a norm. So this is showing data for a 5-minute window. And you can see that for this particular 5-minute window, that one group of servers up there is much slower than normal and actually taking up kind of a lot of time. So that's probably what's causing latency issues. Another visualization that's kind of cool is the same exact data set. And that data set, by the way, is just, it's the same kind of data set you'd feed into something like Zipkin for tracing. It's just a request response with latency from every microservice, and along with an idea of what overall query it came from. So the same data set, visualized a different way, so a different set of Druid queries, is latency tree map by database backend. So by which backend, which data backend is that microservice talking to? You can kind of see pretty clearly here that the two database backends in the lower left are causing some issues. And finally, this is from the same set of graphics, a time series plot of latency quantiles using Grafana. This is using the Grafana plugin. So that's a good segue to talking about the Grafana plugin. This is where you can find it. You can also find it linked at the tutorial at the GitHub that I mentioned earlier. It was written by that same guy that the graphics came from, and it works with Grafana 1.9. This is another visualization from that Grafana plugin. This is using two features of Druid. It's using the top ends and uniques. So this is so the one on the top left is the unique users by device type. So it's sort of top devices by unique users over time. And the setup instructions again for this are in the workshop repo. So the last sort of technical thing I want to talk about is ingestion, how you get data into Druid. I talked a bit about how you get data out of Druid and how you visualize it and what it looks like inside Druid, but I want to talk about how you get it in. So the idea, remember from earlier that you have real-time workers, historical nodes, and broker nodes in Druid. The idea is that data comes into the real-time nodes from a data source. And for a lot of people, that data source is Kafka. Druid has built-in integration with Kafka. It does support other things, but that's one of the more popular ones. There's another kind of use case where you need to pre-process your data a bit before it goes into Druid. This might be if you want to enhance it. Maybe you want to include some other information and join it in. Maybe you want to do some other kind of join. Maybe you want to do some bucketing of something. If you want to enhance it in some way, you can put a stream processor in between your data source and Druid. And these are some popular stream processors. All of those work pretty well with Druid. Samza, Storm, Spark Streaming, and they all work very well with Kafka as well. So the last thing I want to talk about is the future of Druid, where we're going. And I hope this will also be interesting to sort of give you an idea of where the weaknesses are in Druid, because the roadmap and weaknesses are kind of two sides of the same coin. So the first thing is we have a hit list for dependencies. So Druid shows its roots as originally being developed to sort of power this cloud analytics application. It has a ton of external dependencies. Over the past few years, we've sort of been drawing them down. They were sort of depending on random AWS services. Two that are left that we still want to get rid of and haven't done yet are Zookeeper, which it uses for coordination, and MySQL, which it uses for metadata storage. And by metadata storage, I just mean what segments there are and where they're supposed to be located. We also have a simpler architecture. The architecture of Druid right now arose from a lot of experimentation. So over the past few years, we've just tried a ton of different things, seeing what works, what doesn't work. And in a lot of cases, we have the thing that works in there. We also have some of the things that don't work, and they're kind of in different files, and we kind of tell people not to use the one that doesn't work. And that's something that, because we still have the magic 0 in front of our version number, we're at 0.7 right now, we can remove some of that stuff, and we want to do that. One example is that we support 4 different ingestion methods, and there really should just be 1 or 2. The one I mentioned was real-time ingestion from Kafka, but there's also, you can do push into real-time. You also, as a Hadoop ingestion, there's also sort of a file upload. This other thing that I think we should hopefully fix soon is Druid has a concept called the ingestion window period, which is the amount of, it's basically how old data can be before it's allowed to be ingested. So if you think back to the real-time nodes and historical nodes, the real-times are handling all the writes. They have the ingestion window concept where if a write is too old, they won't have any segment to put it in, and they'll sort of drop it. They have metrics that they dropped it, and they log when they dropped it, but it's still kind of annoying. Like, you still want to have the opportunity to stream in like a historical data file, or just have some server be down for a few days and then come back up and send some old metrics and have those be indexed. So we'd like to support that. Currently, the way to work around that is that Druid's batch ingestion does support any time period, so you can upload that stuff in the batches as a backfill. Pluggable indexes would be great. Like I said, we have those concise roaring bitmap indexes built in. We also have one I didn't mention, some experimental archery spatial index for sort of like latitude, longitude type stuff, or any sort of points on the surface. But we'd also like people to be able to build new indexes and make them available as extensions, the same ways you can do now for metrics and query types. And finally, visualizations. So I showed you all those cool visualizations. Unfortunately, only one of them is free and open source, the Grafana plugin. Grafana is nice, but I think that for what Druid is meant to do, which is this really slice and dicey, interactive exploration type stuff, Grafana is a bit too static. It takes a little bit too long to go and click and set up a new chart and set up the drill downs. It'd be nice to have that be a faster process. And also, it lacks a little bit of context, so that context panel I was talking about is not really a thing in Grafana. So I think that it'd be nice to have a dashboard that plays a little bit more to Druid's strengths and lets you do more things. So what I hope you take away from this is that it's cool to think about metrics as event streams rather than time series, because time series are event streams, so it's just as good. But there's also things that are event streams that don't really make sense as time series, like streams of requests, streams of responses, streams of actions. And thinking about analyzing those things as what they are, rather than trying to shove them into a time series model is kind of useful. I also hope you take away that Druid's good for large data sets that you want to query interactively. The supporting infrastructure is a bit complex in current versions. That was the dependency stuff I mentioned, but we're working on that. And it's also, I think, not too bad if you already use Kafka. Because you already use Kafka, you have a good way to ingest into Druid. Also, Kafka requires Zookeeper, so you must already have Zookeeper. So I definitely recommend checking it out if you already use Kafka. And if you don't use Kafka, consider using that because it's really cool. Thanks, everybody. I think there's a little time for questions. Any questions? Yeah. So the question was, can I talk more about the Kafka integration? Yes. So the real-time nodes, the way they work is you tell them where to pull their data from. So you can tell them you want to pull it from Kafka, and there's a Kafka thing that comes with Druid that you use to do that. And it uses the Kafka high-level consumer. So you give it a consumer group ID, and you just spin up any number of real-time nodes, and whatever number it is you spin up, they partition to work amongst themselves.
So what are your plans with Druid regarding Mesos?
The question is, what are our plans with Druid regarding Mesos? So there actually are a couple of people working on Druid Mesos stuff now. It's kind of experimental, but it's cool. There's two sort of efforts there. One is to get Druid running in Docker and to put the Docker in Mesos. And the other is getting Druid running directly in Mesos and sort of spawning nodes, like, having the Druid brokers like spawn more historicals when there needs more data or something like that, like integrating with Mesos more like that. The first thing is, I think, pretty far along. The second thing, the guy that's working on that is more of the stage where he's writing up a list of things that need to change, if possible. Yes?
What is the fault tolerance story for the various storage packages?
So the question is, what's the fault tolerance story for the storage backends? Really good question. For the historicals, the story is that there's always a backup of data on some kind of deep storage. It's pluggable. The two most popular are S3 and HDFS. So if you have Hadoop, you can store your data in Hadoop. If you don't, you can put it in S3. It also supports something backed like Cassandra if you don't have either S3 or HDFS, but for some reason you have Cassandra. So that's for the historicals. For the real times, the story there's the main story there is if you use the Kafka integration. If a real-time node dies, then it can replay what it lost from Kafka. Yeah.
So we didn't talk about the labeling too much or the alerting. You kind of mentioned either whichever one was probably more interesting.
Oh wait, sorry, I didn't hear.
The alerting aspects of Druid.
Okay, so the question was, can I talk a little bit more about alerting? Yeah, so Druid doesn't have any built-in alerting features. The way that people usually build alerting on top of Druid is polling. So yeah, so you have a Druid query, you make it every 5 seconds or 10 seconds or whatever, and if the result looks funky, then send an alert. Yeah.
So when you were talking about the roll-up aggregations, you mentioned that it does rely on extremely times problems, but is it configurable which aggregation function uses for the numeric columns, or is it always some?
So the question is, when you do roll-up, is it configurable what aggregation to use for the metrics? Yes. So any of the supported metrics can be used as aggregations there. So sum, average, min, max, You can even tell it to aggregate over a string column, and the one aggregation supported there is approximate uniques. And you can also do approximate histograms over a number if you want to know the distribution or quantiles later. You can also do 2 aggregations over the same metric, which is pretty common if you want to be able to do a average latency and also a histogram latency.
Can you figure that per column? So sum on one column, average on another, min on a third?
The question is, can you do that per column and have different columns, different ways aggregated? Yes, you can do that. You can imagine it like the result of a SQL query where you have like a select from table, group by, whatever, and then the things you're selecting are like sum latency as latency sum, and then like, you know, average latency as latency average, min latency as latency min, and so the one source column can become many Druid columns if you want to aggregate different ways.
If your data source is in nanosecond resolution, will Druid ever gain the ability to do that? So that's one of my problems with having Druid is that it samples down to microsecond.
Right, so the question is, are we ever going to do nanosecond resolution? So right now we do millisecond because we're storing things as longs, and Druid's written in Java, and that's kind of the most natural thing to do. We're also using a library called JodaTime in a lot of places that is millisecond peak, so those are the reasons. I think that if I was you and really wanted nanosecond, I would multiply everything a lot, and that would probably be fine. I mean, longs are pretty big. Actually, yeah, that would probably be fine. And the other option is to redo the time stuff so it doesn't. I think that replacing the use of JodaTime with something that does nanosecond is the way to go there. And that would be a really cool contribution if you want to talk about that. It's the beauty of being a community project. I can just tell people about that. Yeah.
Are there any plans to have dynamic addition of metrics?
Sorry?
Are there any plans to support runtime addition of metrics? Right now, I think it's metrics are significant.
Okay, so the question is, are there any plans to support runtime addition of metrics? So that could mean 2 things, I guess. One could mean, can I do a schema change at any time? And the answer to that is yes. The other question, so you can do a schema change anytime you want in Druid, and it'll affect all newly ingested data. The other way to answer that might be, can I make that retroactive to old data? And the answer to that is no. And the reason for that is because in that Druid segment format, where things are all column-oriented and stored in the way that it's stored, because of rollup, so because we may take 2 events that were separate and put them in the same row, we actually don't have enough information to blow them back out and reindex them. So the way to do that is to reindex your raw data. So usually most people who use Druid will save their raw data somewhere in some data warehouse. And if they want to go back and add a new dimension or add a new metric that wasn't previously indexed, you sort of go back and reindex your data warehouse. If you want to get that history. If you don't, then just schema change anytime you want. Anything else? Cool, thanks everybody.